Alright, let's talk assembly language. So, one of the cool things about working in assembly language and trying to learn assembly language programming is that you can take an answer that you've come up with and you can tell whether it's correct or not all by yourself. You don't need to guess, or wonder, did I do this correctly or not? When you write code, you can go into a simulator and a debugger like MPLAB and tell exactly what that code is going to do. And this means you can come up with your own problems to work on, to practice, to improve your understanding of how assembly language works and how a microprocessor works, and you can see if your understanding is correct. So let's play around with this for a few minutes. So we've been doing problems in class where we say something like, let's take a high-level language statement like if x equals 0, then result equals 1. And I've given you problems where I say, let's write assembly language code that performs this instruction, right? So this is what I want to have happen. So we might write some code like this. We might say move file register X into the W register. And we know that this updates the status register. This sets things like the 0 bit, the overflow bit, and so on and so forth. So we'll use this to examine the value of X. And we can do conditional branches based on those bits. So I can say branch if this is 0 to, I don't know, let's go to a label called set result. And then down here, I'll put my label, right, set result with a colon after it. And I'll do what I want to do if X was equal to 0, which is set result equal to 1. So how do I do that? Well, we need two instructions. Move the literal value 1 into the W register, and then move W into the file register called result. And that's our code, right? This is our solution that we would turn in on a homework or something like that. And we can go back and reread this to see if this looks really correct. But since we wrote this ourselves based on the goal of performing these operations, this is what we came up with. Chances are, if I go back and I look at this code, I'm going to think about it the same way I thought about it when I was writing it, and I'm going to come to the same conclusions, which is like, yeah, this looks good, this is probably correct. Let's take out the guesswork. Let's actually put this code into MPLAB and see what it does. Okay, this will take some patience and some effort and some diligence, but if you do this, you are guaranteed to know exactly what this code is going to do. And the more you do this, the quicker you get at it. Okay, so let's go into MPLAB, and you've done this a number of times now. So let's make a new project. We'll do a standalone project. We'll put in pick 18F1220. We'll go with a simulator. We'll go with MPASM. We'll call it Debug Video 1. And then I'm going to right click up here where it says Debug Video 1. I'm going to say new and put in an ASM file. I'm just going to call it main. It doesn't have to be anything in particular. And let's go ahead and start writing some code. So I'm going to include p18f1220.inc. I don't think I need it, but it never hurts to have it in there. I'm going to go ahead and do radix decimal. Right? Normally I stick to hexadecimal base 16 in class, but we're going to be comparing numbers today, so I'm going to eliminate the added complexity of dealing with hex, and we'll just do everything in good old base 10. Now we're going to have a pair of file registers to work with. One is called X, one is called result. Let me define those up here. So I'll say X equals, and let's put that at location 20, and let's put result, and let's put that at file location 30. Alright, I'm going to do origin 0. That's where the start of my program is. Okay, this is remember, location 0 is where the processor starts to execute your code. So you better start writing your code at location 0. That's what the origin 0 statement says. Alright, and what did we decide to do? Let's put X into the W register. So move F, X comma 0. And I'm going to put some comments in here. Update status bits based on value of x. And then we said if it's 0, let's go to this label set result. So branch of 0 set result. And here's my set result. I'm going to put a label here. So go here if we want to set result equal to 1. And this is because x was equal to 0. Alright, how do we set x result equal to 1? Put a 1 into W, put it into result. So move LW1, move WF, result. Alright, and we should be done. So we'll put an end statement out here. And let's see if we can assemble this without errors. Build successful. That's good. Alright, let's look at our variables. So I'm going to get rid of most of these. I'm going to keep W register because I want to look at that. I'm going to add a variable at location 20 hex. So I'm just going to click over here, do 0x20 and enter. Going to click in here until it lets me type, do a 0x30 and enter. And I'm going to put a breakpoint at my first executable statement. I can't put it here because this is not an executable statement. This is not an executable statement. This is the first statement that will execute. So I'm going to put my breakpoint there, which means the simulator will stop before I've even done my first line of code. So let's go ahead and run. And it tells us breakpoint hit at line 8, user program stop. That's right here. Now the line that's green is the line that's about to be executed. Let's look at our variables. Everything is 0. Okay. Remember, this is x, this is result. We're trying to say if x equals 0, set result to 1. So let's see if this works. So first thing we're going to do is move x into the W register. And x is 0 and W is 0. This doesn't look like it's going to do anything, but our goal is to update the status bits based on the value of x. Remember, up here we can see the status bits. N overflow 0, decimal carry, and carry. The z is lowercase. That means the 0 bit is a 0. When we do this move, so let's just step 1 instruction. I'll do this step into. And the only thing that changed is this z bit went uppercase. That means the processor detected that I just did something with a value of 0. In other words, it noticed that x was equal to 0. And now when we do our conditional branch, branch of 0 set result, we have confidence we're going to end up taking this branch. So let's go ahead and step once more. Sure enough, we jump down to set result. So here we should put a 1 into the W register. Let's execute that 1 instruction. And you notice this line went red. The W register is equal to 1. And now we say move that into result. Result is location 30. Let's step one more instruction. And guess what? The W register should have gotten copied into result. So something is wrong. Alright, what's going on here? Okay, so we step once more and the W register got copied into result. Result is equal to 1. Hey, it looks like our code works perfectly, right? So, if x is equal to 0, set result equal to 1. Yeah, that worked great. Are we done? No, not yet. Because, you know, maybe our code always sets result to 1. Maybe it sets result to 1 if x equals 0 or if x is equal to 11, right? We need to test as many cases as we think it takes to convince ourselves that this works. And we've tested half of this condition. If x is equal to 0, this happened. But let's make sure if x is not 0 that this does not happen. So how are we going to do that? Well, let's modify our code a little bit. So I'm going to put some extra stuff in here. To let us load interesting values into x and result. So let's say move LW, let's put a 0 into x. And I'm just going to put a 17 into result for no particular reason. All right, this is all just setup. This is like a test bench. This is like wiring up a proto board to see if your circuit works correctly. This is preamble. Okay, here in particular I'm setting x to 0 and result to 17, and now I'm going to execute that same code to make sure that that result gets set equal to 1. So let's go ahead and rebuild this, and I'm going to leave my breakpoint down here. Let's go ahead and run this code. Let's look at our variables. So yeah, we can confirm x is 0, result is 17. Okay, let's move x into the W register. We see the 0 bit got set, branch of 0 set result. Here set result is going to put a 1 into W, and then it's going to copy W into result, which is down here. Result was 17 so far. When we execute this instruction, result changes to 1. Hey, our code looks great, right? I started off with x was 0, result was 17, and after I finished this, since x was 0, result became 1. Let's do one more test. Let's make x non-zero. Let's set x equal to 1. Let's build this. And you notice once you've done this a few times, the cycle of making a change, building it, stepping through the simulation starts to get very quick, right? So let's go ahead and stop this. Let's build it. Let's run it. We'll stop right down here. Let's look at our variables. And in this case, x is a 1. Result is 17. So we're going to move x into 0. There are 0 bits not set. We're going to say branch of 0 set result. Well, it should not take that branch. But look what happened. It's down here where we're saying move LW1. And when I do that and this, my result changed to 1. So something's wrong, right? X was not 0, but at the end of this, my result was still equal to 1. So blink, stop, go back, rerun, watch what happens more carefully. Okay, so what am I thinking here? I'm going to put x into 0. That's going to update the status bits. Yeah, my z is still lowercase there. My status bit is saying this is not 0. And I say if the result is 0, I should branch to set result. It should not be taking that branch. But yet it ends up at set result. Okay, why is this happening? Because assembly language code is sequential. And I can tell that to you in class. I can explain it a dozen different ways, but until you've sat through and actually worked something like this yourself and puzzled over what's happening, it's not really going to sink in what that means, right? So I'll tell you anyway. What that means is that each instruction, after it's executed, the processor moves on to the next instruction in memory. Even though we didn't branch to set result, we fell through, right? If you don't branch, you execute the next instruction in program memory, which is move LW1. And so in this case, whether x is 0 or not, I still end up down here setting result equal to 1. Alright, so here's a quick fix that I've seen some people do, which is to go ahead and throw a no-op in here. So let's put a no-op in there, let's rebuild, let's start executing, look at our variables, move x into 0. If it is 0, we should branch to set result. Well, 0 is clear, so it should not take the branch. And sure enough, it skipped the branch. Okay, this is good, this is progress, right? We said if x is 0, let's branch to set result. Well, we started off with x non-zero, and it skipped the branch. So our conditional branching is working perfectly. And we're down here and we're doing the no-op. But what's going to happen next? It's going to fall through and execute the next instruction in memory. All right. So that's where the light bulb goes off sometimes, which is that even though I didn't branch to set result, I fell through to it. All right. So what should I have done? Let's try something like this. Let's change this to branch to do nothing. All right. Now one thing I'm going to have to do that's just a little peculiar because of the way I'm simulating this, I can't have a label without any code after it. If I try to branch here, my simulator's probably going to get a little freaked out. So I'm just going to put a no op down here, just so that I have a place to stop and look at things after I do this branch. Okay, so my logic here is if x is 0, I will come down to set result, which will set result equal to 1. Otherwise, I will skip that conditional branch, and I'll just branch down here to do nothing. Alright, so let's build that. Let's start simulating it. And remember, I'm setting x equal to 1, so I'm going to say branch of 0 result. The branch does not happen. It should branch to do nothing, and when I get down here, result is still 17. That's good. Okay, let's make sure we didn't break our original version when we had x equal to 0. So let's change that code, stop the simulation, rebuild it, start the simulation, look at our variables, start stepping. Move x into the W register, branch of 0, set result. We wanted to take that branch, and sure enough it does. It comes down here, puts a 1 into W, moves that into result, and now results equal to 1. And we end up back at this, end of our program. Alright, so this seems to implement this code. So we needed this extra step, which was branch to do nothing, and then do nothing was down here. Alright, let's keep going. Let's try this. If x equals y, then result equals 5. Okay, so I'll add a new variable in here. Put a variable y in there, and I will put in some new watches. And I'm editing this one because I want these to be in order. Alright, so I got 3 watch points now, 20, 25, and 30, as well as W reg. And let me put some things in here. So let's set x equal to 0. Let's set y equal to 0, and let's start off with a result equals 17. Why not? Okay, and let's test this code. Well, how do we do this? We've seen this trick, which is to say if x equals y is the same thing as saying if x minus y is equal to 0, then result equals 5. And we just wrote some code that said, if something was equal to 0, do this thing. So what we want to compare to 0 is simply a result of x minus y instead of, just the value of x. So how do we do this? Let's say something like move f x comma 0. Let's put that into the W register. And then let's subtract y. And let's say if this is equal to 0, we want to set the result equal to 5. So branch of 0, set result, otherwise branch to do nothing, and then set result. Let's set result equal to 5. So move a 5 into W, move WF into result, and then down here is our do nothing. Alright, so there's our attempt at our assembly language code. So let's play with this. Okay, so let's move x comma 0. let's calculate x minus y, and branch at the 0 is set to set result, otherwise do nothing. And let me put my source code up here that I'm trying to implement. Okay, that's what I'm actually trying to write. So put x into w, subtract y. If it's 0, let's come down here to set result, which puts a 5 into w and puts that into result. Alright, and we're starting off with x and y are 0, and result is 17. Breakpoint set at our first move. Let's go ahead and build this. Let's go ahead and start it. Look at our variables, and let's single step. Okay, so we're putting an x into the w register. W is 0. We're going to subtract y. And this should be 0 minus 0, right? So the result should be 0. And if we look up here, yeah, our 0 bit is set. Branch of 0, set result. Does it do it? Yes, it comes down here to set result. This will put a 5 into w. There's our 5. And then it'll move that 5 into result. And guess what? Result got changed to 5. And we're at the end of our code. Okay, so far so good. If x equals 0, set result equal to 5. Fantastic. Alright, let's make sure it works if x and y are not the same. Alright, so let's try a different test case. Let's set y equal to 10. Alright, stop, rebuild, start, look at your variables, let's single step. Okay, now x is 0, y is 10, result is 17. Okay, our hope is that this if statement does not cause result to change. Okay, so we're going to move x into w. There's our 0. We're going to subtract y, right? And we've got a 0, branch of 0, set result. Well, our 0 bit is not asserted, so we believe this is not going to fire, and sure enough we end up saying branch to do nothing, and result down here did not change value. So our code looks great, right? If we made these both 0, it set result to 5. If we made this 0 and non-0, it set result to, it left result alone. Are we done? No. Okay, so you want a test plan. You want to figure out what things am I going to try to do to see if this code works. Well, there's some other cases to try. Because 0 is always a special number, right? So let's set x and y equal to each other, but let's make them, you know, some unusual value. So let's stop this. Let's set x equal to 10 and y equal to 10. And in this case, you know, x and y are equal, so result should get changed to 5. So let's build this, and let's run it. Look at our variables, start single stepping. And we'll step through. X goes into w, subtract y, and it branches down to set result. So it puts a 5 into result, and we're done. Alright, well, you know, that looks good. But there's actually a huge problem in our code, and you probably missed it if you did this as quickly as I just did it. So one of the problems with this is that, you know, it's very tedious to step through things one instruction at a time. But, you know, if your code is perfect and you do that, you're going to end up feeling really great because, yeah, I've got this code completely nailed down. This is fantastic, right? It's really worth, especially in the earlier stages of figuring this stuff out, going through this as carefully as possible, one instruction at a time. So let's stop this, rerun it, and step through this a little more carefully. So we're looking at all our variables. WReg is 17 because we use that to set the value of result. That's fine. Okay, let's put x into the W register, so we'll execute that. X just changed to 10. X was 10. WReg just changed to 10. That's fine. Now we're going to calculate x minus y, so we're going to do 10 minus 10. Let's execute that one instruction. Anytime you see red down here, something has changed. Well, the simulator is telling us, guess what? Y just changed to a 0. Is that something we wanted to have happen? Probably not. We were calculating x minus y so we could tell if x and y were equal. Well, we just introduced a side effect. In making this comparison, we changed the value of y. Now, our branch of 0, our setting of result equal to 5, that's all going to work fine. But when we're done, and we come down here to the end of our code, x is still equal to 10, but y has changed value. And that's a huge problem. And it doesn't jump out at you if you just kind of look at the end result, which is, yeah, I wanted this to be set to a 5, and it did. But we inadvertently changed the value of y. Okay, why is this a problem? This is like calling up your bank and saying, hey, do I have $100 in my bank account? And they check, and they say, yes, you do. And you say, thank you. But in the process of checking, they removed $100 from your account. Right? So you had $500 in your bank. You call up your bank. Do I have $100? They say, yes, you do. But now you've only got $400. That's not what you wanted to have happen. Okay, there's this fundamental difference between comparing two things and doing an arithmetic expression. And nothing in this statement says change the value of y. This says compare the values of x and y, and if they're equal, change the value of result. But nothing in here says change the value of x or change the value of y. Okay, that's a side effect that we do not want to have happen. And why does that happen? Because subtract WF by default changes the file register. All you got to do is put a comma 0. Put the result back into the W register, and this problem goes away. So let's try that. Okay, so we'll put a comment on there saying don't change y. Let's build that. Let's simulate it, look at our variables, single step. Okay, now x and y are both 10, and result is 17. And I'm going to put x into w, so w changed to a 0. I'm going to subtract, I subtracted y. Let me start this again. Alright, I'm going to put x into the w register. That makes w a 10. Now I'm going to subtract y from the w register and put the result back into w. The only thing that changed was w. X is solid, y is solid. Result hasn't changed yet. Okay, this is what we want. We don't want to change variables unless our intent is to change them. W we can do whatever we want with. It's a temporary register. It's a working register. That's what the W stands for. Okay, so I updated the value of W as part of figuring out if something was 0, which it was. This will branch to set result. We'll put a 5 into the working register, and then we'll move that into result. And now x and y are unchanged. Results equal to 5. So our code works fine. Alright, let's try one more statement. Let's do the following. If x is less than y, then result equals 5. And we're going to change this into the equivalent form if x minus y is less than 0, then result equals 5. Because we have a conditional branch called branch if negative, meaning less than 0. So we're going to take the same code we had before, but we're going to tweak it just a little bit. Instead of saying take x, subtract y, and branch if the result is 0, we're going to say branch if negative to set result, which will put a 5 into result. So this shouldn't take a lot of tweaking. So if x is less than y, then result equals 5. So all I'm going to do is I'm going to change this to a branch if negative. And I'll put a comment here, branch and set if x minus y is less than 0, which is the same thing as saying x is less than y. Alright, so I will build that. I will start simulating. I'll look at the variables. And we're starting off with x and y are both 10. Okay, 10 is not less than 10. 10 is equal to 10. So this first test case should not change the value of result. Put x into w, subtract y, we end up with a 0. Branch if it's negative, set result. Well, we can see up here negative is not asserted, so it should not take this branch. It'll branch to do nothing. Result did not change. So far, so good. Alright, now we didn't use special magic values like 0. So let's try our next test case. Let's set x equal to 9. I'm setting x equal to 9 and y equal to 10. So this is 9 and 10. 9 is less than 10. This should change the value of result. Alright, let's build that. Let's start to simulate, look at our variables, and let's step through this very carefully. We're going to start off by putting x into the w register. So x is 9, so w is equal to 9. Now we're going to subtract 10 from that, which should give us negative 1. Guess what? We did x minus y, we ended up with positive 1 instead of negative 1. And you can see our negative bit is not asserted. We're going to say branch if negative, set result. This is not going to take the branch. It's going to branch to do nothing, and we did not change result. Uh-oh. Something went wrong. We said x equal to 9, y equal to 10. X is less than y, but it did not set our result. What in the heck happened? Well, I don't know, but the answer is right here. So let's just go ahead and re-simulate this. And let's proceed carefully, right? Something went wrong. We expected it to branch right here, and it didn't. So something went wrong before that. Okay, what are we trying to do? We're trying to put x into the w register. Let's step that one instruction. Yeah, x is 9, right? That's what I wanted to set. And w is equal to 9. Now we're trying to do x minus y, and y, we set it to a 10. I can look down here, y is equal to 10. I should be doing x minus y. 9 minus 10 is negative 1. But when I execute the subtract instruction, I get positive 1. Okay, maybe something jumps out at you, maybe it's not clear at all. Go back to the data sheet. So you can go through the full data sheet, or you can do the quick reference guide. And let's look at the subtract WF instruction. And you may have looked at this 20 times, but if you look at it another time, subtract W reg from F. Subtract W reg from F. So sub WF Y says subtract W reg from Y. In other words, do Y minus W reg. And W reg we're setting equal to X. So we're actually calculating Y minus X. Well, X is 9, Y is 10. Y minus X is 10 minus 9, which is 1. That's exactly what we asked it to do. It's not what we wanted it to do. We wanted it to do X minus Y, but guess what? The instructions we wrote actually told it that it should do Y minus X. Alright, we just learned a bunch of things. We just learned about the sub WF instruction. We learned that sometimes if we're expecting a negative and we get a positive, we should look at the sense in which the subtraction was done. Right? So how do we fix this? Let's just change these around. Let's put Y into the W register and subtract X. Sub WF says subtract the W register, which is Y, from X. So this should do X minus Y. Alright, let's rebuild. Let's simulate. Let's step. Put Y into the W register, that's 10. Subtract X from it. Subtract Y from X. Right? So this should do X minus Y. And hey, the W register is -1. Well, it's 255. We work in 2's complement, right? If you look at it in hex, it's 8 ones. That's the binary equivalent of -1. And we can check up here, our negative bit is set. So when we say branch if negative, set result, that'll come down here, set the result to 5. Our code works now. On the other hand, if we set x equal to 11, build that up, run it. Now x is 11, y is 10, x is not less than y, it should not change the result. So let's step through, let's do our subtraction, and the negative bit, oh I messed up, I said x equal to 1. Well, okay, so we can do this test. X is 1 and y is 10, x is less than y, it's going to go ahead and set our result. So I messed up my test case, but the code still did the right thing. But what I want to do is set x equal to 11. So let's do that final test. Build this up, simulate it, start stepping, put y into the W register, that's 10, subtract y from x, which was 11, there's our difference is 1, branch if negative, set result, it's going to branch to do nothing, and we're good. X was not less than y, so result did not get changed. Alright, this was supposed to be a 10-minute video. I don't know what we're up to now, but it's way more than 10 minutes. This is how assembly language goes. Okay, it's low level, it's minute, it's a lot of detail. But if you are willing to work with it at that level, you can answer all of the questions. You can unravel all of the mysteries, right? Everything that you need to know is available inside here, looking at variables, looking at status bits. And the more you do this, right, the better you get at it. You can do things like this. Status is a built-in file register. I can say move F status. That's not going to do anything. But guess what? If I build this up and I start simulating, right? I can go through, I can look at my variables and so on and so forth. I can see my status bits here, but because I refer to status in my source code, if I just hover my mouse over it, it will show me a nice little picture of my status bits, right? And I can see here under 4n, there's a 0. That's telling me clearly my negative bit is set to 0. And now when I execute the sub WF instruction, right, n is still 0, I can confirm that by looking up here, look at the status bits, n is 0. Now if I said y equal to 20, build that up, step through, right, so hover over here, the n bit is a 0, do my subtract instruction, and now if I hover over status, you can see that red 1 under the n, my negative bit has been set, which is why this branch if negative is going to jump to set result. And all of this stuff, setting up fields down here, if you want to look at something in binary, you can right click on anything in the header and check the binary box, and now we've got a binary field. And we can make it larger if we want. Being able to stop and rebuild and simulate and come down to variables, well, that takes a long time in Lab 1, right? By this point in the course, you've done it more than a few times. It starts to get faster. This is all just practice. And, you know, different environment, different class, different job, you'll have different tools, but the same kinds of things going on. So spend the time working on this, right? And I'm absolutely happy to help you with any of this. I'm absolutely happy to help you with questions. But my suggestion is, right, don't try to just watch videos or read things in the book or stare at things on a piece of paper. Actually jump into the simulator and start stepping through code. Start looking at what's happening as code executes. And this is really useful when we start, you know, writing code for timers and interrupts and all of that stuff that we're moving into in the end of the course here. This is your best friend, right? This simulator. And you can do whatever you want, right? Just make up a problem, try to code it, change something and see what it does. right? And when you do this as, laboratory experiment instead of, textbook exercise, it's usually a lot more meaningful. It sinks in, it registers at a deeper level, and frankly, I just think it's a lot more fun. It's interactive. So anyway, that's a long, stretched out detail about things we can do with MPLAB, but hopefully that helps. All right, thanks for listening. Bye.